Okay, so we're in P3, the vectors chapter, and we're going to be looking today at the scalar product in particular. I'm going to do it in three basic steps. First, how do we do it? How do we compute the scalar product? Second, what is it? What does it actually mean? What does it tell us? And third, why does that work? Okay, so let's start with one. That's kind of the simple thing. Let's say I've got two vectors here, the vectors A and B. So A is 4, 1, 3, B is 3, -2, 5. Then how do I find the scalar product? Well, I write it as A dot B. So notice there's a dot there. We sometimes call the scalar product the dot product. And rewrite these vectors as well, just to make it a bit more clear. So 4, 1, 3 dotted with 3, -2, 5. How do I compute this product? Well, what I do is I take the two I components, the 4 and the 3, and I multiply them together. So 4 times by 3 is 12. Then I take the two j components and multiply them together. So 1 times by -2 is -2. And then I take the two k components and I multiply them together. 3 times by 5 is 15. And then once I do that, what I do is I add these guys up. So I do 12 plus -2 plus 15. So what's that going to give me? Well, 12 minus 2 is 10, plus 15 is 25. So the scalar product of A and B is 25. Now notice that what we've got here is we've got a scalar. Okay, we've got a scalar. So the scalar product takes in two vectors, A and B, and returns a scalar. That's why it's called a scalar product. So how do we do that? Just recap. We multiply the i's, multiply the j's, multiply the k's, and then add these guys up. Let's do one more example. So I think it's relatively straightforward. Let's say I've got 5 minus 2, 4, dot producted with 3, 8, 1. How am I going to do this? Well, I do 5 times by 3, which is 15, plus -2 times by 8, which is -16, plus 4 times by 1, which is 4. 15 minus 16 is -1, plus 4 is 3. So that's the scalar product of those two vectors. Now, okay, let's return to our original questions. We know how to do it now. The question 2 is, well, what is it? What does it mean? Well, the scalar product is essentially this. It tells us the projection of one vector onto another, right? So the key word here is projection. And you're probably wondering what on earth that means. Projection is kind of like the shadow that one vector is going to cast onto another vector. So we're going to start with looking at unit vectors. So vectors of size 1. So let's say what we got here is we've got a vector there and a vector here. All right. And there you go, one vector, another vector. Why don't I call this vector here A? I call this vector here B, okay? And there's an angle between them that I'll call theta. Now, the projection of the vector A onto B is going to be this thing. So let me try to draw out like that. I think I'll draw with dashed lines. So it's going to go like that. Right, so imagine drawing a kind of a line that goes perpendicular from the vector B all the way up to the point of A. Well, the projection is going to be that length there. Right, that is the projection of A onto the vector B. Okay, so I'll call that there. That is P. I'll call it P. The projection of A onto B. Okay, and we can also think about the same way of the projection of B onto A, right? So if I was to take the vector B, I was to try to do this, something like that. Okay. Again, this is a right angle. Then this length here is the shadow that B casts upon A, if you like to think about it that way. And so we can talk about that being P as being the projection of the vector B onto A, right? So here, this is the projection of A onto B. This is the projection of B onto A. Sorry, I falsely labeled that P there as a vector. Of course it's not, it's a scalar. Beg your pardon. All right. Now then, in the case where A and B are unit vectors, right, so they're both vectors of size 1, so both A and B have got a magnitude of 1, these two projections are going to be the same, aren't they, right? So the projection of A onto B is the same as the projection of B onto A. That's an important thing to note at the start, because we can say that the scalar product of AB, so A dot B, is going to be the same as B dot A, because these two projections here are identical. Now let's try to show why this works, and we're going to show why it works using a two-dimensional example. Okay, so let's go down. I'll draw this out one more time, I think. Here is vectors A and B. So that's A hat. This is B hat. Okay, and we'll say we've got a coordinate frame here as well. This is kind of like our Y and our X. Okay. And we will define the components of A like this. Right, so that's like the vertical component of A. I'll call AY. And this is the horizontal component of A, which I'll call AX. So this is AX, and this is AY. I'm going to say that the angle that A makes with the x-axis is angle alpha. Okay, and we're going to do the same thing for B, so I'll use a different color. I'll use yellow. Let's split that up into horizontal, vertical components like that. Okay, so the horizontal component of B, I'm going to call BX. And the vertical component of B, I'll call BY. And the angle that B makes with the x-axis, I'm going to call beta. Now we can do a little bit of trigonometry here, right? Because we've got a green triangle and we've got a yellow triangle. So let's just use the green triangle for the moment. We can say that sine of alpha is going to equal to opposite AY over the hypotenuse. And this is a unit vector, so the hypotenuse is 1. So we can write that out and say that AY is equal to sine alpha. Let's just double check that again. Sine alpha is opposite AY over the hypotenuse, which is 1. So AY is sine alpha. We can do the same thing for AX. This is the adjacent side. So cosine of alpha will equal to the adjacent AX over the hypotenuse, which is 1. So we can now write out AX is equal to cosine of alpha. And we can do the same thing for B, right? We can say that BY is equal to sine beta. And we can say that BX is equal to cos beta. Now then, let's think about our projection. Now we're going to do the projection of A onto B. So I'm going to draw that down there like that. Okay, and so I'm going to highlight this in red. What I now want to do is I want to find this length here, which is the size of the projection of A onto B. Well, how can I do that? I can use trigonometry again, because I've got another right angle triangle here, and the P is the horizontal side, right? So, sorry, the adjacent side. So I can say that if I was to define this angle here as theta, right, the angle that A makes with B, or the angle between A and B, then I can say that cosine theta is equal to the adjacent side P divided by the hypotenuse, which is this length here, which is 1, because remember we're using unit vectors. So let me just restate that. The cosine, we're looking at this particular triangle here, right, that triangle there. The cosine of this angle is equal to the adjacent side length, which is P, our projection, divided by the hypotenuse, which is 1. Okay, now then, we can therefore state that P is just equal to cosine of theta. Well, what's theta? Theta is the difference between these two angles, alpha and beta. So we can write cos theta as being cos of alpha minus beta. And if we know our trig identities from elsewhere in P3, then we can rewrite this and say this is equal to cos alpha cos beta plus sine alpha sine beta. And we just go up to the top and we realize, well, we already know what cos alpha is. That's equal to the AX. We know what cos beta is. That's equal to BX. We know what sine alpha is. That's AY. And we know what sine beta is. That's BY. What we can write here is this is the same thing as AX times by BX plus AY times by BY. And what is this? Well, this is the same thing as having ax, ay, dotted with bx, by. In other words, for 2 dimensions, what we've shown is that the size of the projection is equal to the scalar product of these 2 vectors. Okay? And in the next video, what we're going to do is we're going to explore how we can build on that for vectors which are non-unit vectors, so that we can eventually arrive at the formula, which you will know, which is a dot b is equal to the magnitude of a, the magnitude of b, times by the cosine of the angle between them. But we'll return to that in the next video.